Dear students, welcome to the video lecture on simple harmonic motions. In the last class, we have learned what is simple harmonic motion. We have derived the equation for simple harmonic motion, evaluated the displacement of the simple harmonic motion, and understood the meaning of the force constant. Today we will learn one more concept of the simple harmonic motion, or one more concept which will make us to understand simple harmonic motion in a better way. So in the earlier classes we have defined a simple harmonic motion as a special type of periodic motion in which the acceleration of a particle is proportional to the displacement, and it is pointing towards the equilibrium. This is how we have defined it. But we can define SHM in another way also. SHM is also said to be a projection of a uniform circular motion on the diameter of a circle. So what is the meaning of this? So it is a statement that is given to you. It is a thing but the projection of a uniform circular motion. Projection of a uniform circular motion on the diameter of a circle. On the diameter of a circle. So what is this? Let us understand what is the meaning of SHM and how it is represented like this. I have a certain particle which is executing a simple harmonic, which is executing a uniform circular motion. Okay, so I have a mass which is executing a uniform circular motion. So this particle, when it is moving in a uniform circular motion, it is having a projection. It is having a projection on the diameter y dash. Let us take that projection as like this is the projection on the diameter. So this is the diameter. Okay, so the projection is represented by n. This is the projection. Okay, now as the mass, I can say it as a mass. As the mass moves in a circular manner, the projection n will move from origin, reaches y, comes back to origin, goes back to y dash, again comes back to origin O. That means when the mass is making one circular motion, the projection would have made one complete oscillation. Let us check it. So I will write here. Okay, when the mass makes one complete uniform circular motion, or when it completes one circle, the projection, its projection would have completed one oscillation. One oscillation. Got it? So what happens when the projection is completing one oscillation? The projection is such that it is having oscillation such that they are similar to the simple harmonic motion. Let us check it. Okay, so what happens? The mass is at x, the projection is at O. So I will take it as P, the point P. Okay, point P is at x. Now initially point P is at x. Whenever it is at x, the projection n, I will take the projection as n. Okay, the projection is at origin. So this is the initial point. This is the first quadrant. N is at origin. As the point P moves towards y, look at this. As the point P slowly moves towards y, the projection will also move towards y. The projection n will also move towards y. For example, if the point P is here, the projection will move towards y. So this is the projection n. Now it is moving in the upward direction. It is moving in the upward direction like this. Okay, it is moving in the upward direction. N, which was at origin, it is moving in the upward direction. Look at the P was at x, N was at O. P is moving in the circular manner. Therefore, the projection N will move towards Y. Okay, and at exactly at when when P is at when P is at Y, when P is at Y, the projection is also at Y, and they coincide. Okay, at this point, P and N, they coincide. Okay, so in the first quadrant, as the point P moves, the projection N moves in the upward direction. Okay. Now what happens once the point P enters into the second quadrant? Once the point P enters into the second quadrant, so this is the case when it is in the first quadrant. When it is in the first quadrant. Now when the point P enters into the second quadrant, when it is entering into the second quadrant, once it enters into the second quadrant, okay, the point P as point P moves from Y, point P moves from Y to X dash. Look here. Earlier it was at Y, now it is moving towards Y dash. So this is the point P now. It is moving towards X dash. The projection of this point, now if you look at the projection, it is moving downwards. The projection N is moving downwards. Now it is moving in the downward direction. The first quadrant is moving upwards, and the second quadrant is moving from Y towards O. So therefore, the projection N is moving from Y towards O, towards the origin. Y towards the origin. And at exactly as P is at X dash, N will be at N will be at origin. So it comes back to the origin. So when point P is at X. Got it? After that, what happens? It is entering into the third quadrant. Okay, so once it enters into the third quadrant like this, it is in the last case the point P was here at X. Okay, the projection is at N now. Now what happens? It is entering into the third quadrant. Once it enters the third quadrant, its projection now moves in the downward direction, negative Y. So this is the downward direction. It is moving in the downward direction like this. Okay, it is moving in the downward direction. Okay, it is moving in the downward direction. Got it? So as the point P, okay, I will write here, as point P moves from X dash towards Y dash, the projection N moves from origin towards Y dash, towards Y. The projection N moves towards Y dash. Okay, got it? This is the projection N. Now whenever the point P was at X dash, the projection was at N. When the point P enters into the third quadrant, the projection will move from origin to downward direction. Okay. After that, when the point P is at Y dash, is at Y dash here, and the point P, this point P is now at Y dash. What is the corresponding projection? The projection will be at Y dash. The projection will be at Y dash. Therefore, the projection is N. N is also at Y dash. Therefore, at Y dash, both P and N, P and N, they coincide. At similarly here at the point Y, both P and N, they coincide. They coincide. Okay. So after that, it enters into the fourth quadrant. It enters into the fourth quadrant. It enters into the fourth quadrant. So once this enters into the fourth quadrant, okay, it's like this. So this is the fourth case. So when it is in the fourth quadrant, okay, when it is here, the particle is in the fourth quadrant, its projection, okay, will move from y dash towards origin. So therefore, as, look here, you can make it out. This is the point P. Now the point P is in third quadrant. What is the projection? The projection is at y dash earlier. Now it is moving in the upward direction. It is moving in the upward direction. Got it? So therefore, I can write here as point P moves from y dash to x. This is the point P. It was here. It is moving towards x. The projection N is moving from y dash to origin. The projection N is moving from y dash towards N. And at P, at x, exactly at x, whenever it is at x, the projection will come back to is at origin O, is at origin O. So therefore, this point P, when it comes back to this position x, okay, the point P, when it reaches the position x, the projection would have come back to the point N. So therefore, the mass, when it makes one complete uniform circular motion, this point P, look here, this is the point P, okay, so this is the point P, okay, you can look here, this is the point P. So the point P is moving in a circular manner like this. This is the point P which is moving in a circular manner like this. Okay. The projection, this is the projection. The projection will move from origin. It goes back to the point Y. After that, it comes back to the origin. From origin, it goes back to negative direction and it goes back. So therefore, it makes to and fro motion. Okay, to the point? Clear? So therefore, as the point P, as the mass M makes one complete uniform circular motion, its projection N would have made one complete oscillation. It is making one complete oscillation. So therefore, the projection is actually, keep in mind, is exhibiting a simple harmonic motion. Okay, it is actually exhibiting simple harmonic motion. So here, instead of projection N, if I have a projection N, if I have that projection N, if I replace with some particle, I have taken one particle in place of projection, then this particle would execute simple harmonic motion under some influence. We're getting the point? So the projection, look here, the projection what you have, this projection N, okay, this projection N would have made one complete oscillation when the point P makes one complete revolution. Therefore, the projection is making to and fro motion, or it is making oscillations. Okay, so therefore, when the projection is making oscillations, if I replace that projection with the particle, what I can do is I can replace the projection with the particle. Once I replace the projection with that particle is set to execute a simple harmonic motion under the influence of some energy or some force. Okay, so this is the reason why we say that a circular motion is a type of SHM. Circular motion is a type of SHM. Okay, now we can determine the displacement of a particle. Displacement of a particle using this concept of circular motion. Okay, so I have a point, I have the mass at point P now. Initially it was at initially initially the point initially the point P was at X. Now what has happened? It is moved to a new point P. So the mass was at X. Now it has moved to a new point. Okay. Now the once it is moving in a uniform circular motion, the circle has a radius. The circle has a radius equal to A. This is the radius of a circle. So therefore, when the mass was at X, it has moved a certain distance in time t. Distance means it has described a certain angle theta. This is the angle theta. This is the angle theta. You're getting the point. It has described an angle theta in time t. So therefore, I can say that it is moving with a certain angular velocity. It is moving with a certain angular velocity. So the point P is actually moving in a angular velocity omega. So this omega can be given as theta by t. Theta is the angular displacement. Theta is the angular displacement in time t. In time t. Therefore, I can write this omega. Now, to evaluate the displacement, how to evaluate the displacement? Now, as I told you, the projection of P is this much. This is the projection. This is the projection. This is the projection of P. This is the projection of P. Okay. The point P is making a projection N. So this is the projection N. Okay. So I want to check this displacement. No, therefore this is the displacement Y. Okay. To find this displacement, okay, we will use simple geometry. Okay. Now we know that if this is theta, the angle described by the particle is theta. This is the angular displacement. Then from simple geometry, I can write this angle as also equal to theta. Okay. And OP, I can write OP is equal to A. Why? Because it is nothing but the radius of a circle. It is nothing but the radius of a circle. Now from the triangle NOP, so if this is theta, this angle will also be theta. This is from simple geometry. So therefore from the triangle NOP, so then is the projection. So NOP, so from triangle NOP, I can write sine theta is equal to ON divided by opposite side divided by sine theta. You can find it as opposite side divided by adjacent side. Opposite side is ON, opposite side is ON, adjacent opposite side is ON, divided by hypotenuse is OP. So divided by hypotenuse, it is OP. Okay, so I might, okay, fine. So ON by OP. So ON is Y. So I can write it as ON is equal to Y is nothing but displacement. OP is nothing but the radius of a circle. I can take it as A. So therefore I can write sine Y is equal to, if rearrange it, it is Y is equal to A sine theta. Now here sine theta, how you evaluate from this triangle? It is opposite side divided by hypotenuse. Okay, not adjacent side. If I told adjacent side, kindly correct it. Okay, it has ON opposite side, OP the hypotenuse. It is y is equal to a sine theta. I can rewrite it as y is equal to a sine of theta. What is theta? Now look here, omega is theta by t. Therefore, I can write theta is equal to omega t. So why? Because you know that theta, we know that omega angular velocity is equal to theta by t. Therefore, theta is equal to omega t. So therefore, this is the equation for the displacement. And here, A is the new term that you have. Of course, A is already used. A stands for the radius of a circle. Okay, A stands for the radius of a circle. Now here, omega is the angular velocity, t is the time taken, and A is the radius. You should not call it as a radius. It is actually the amplitude of the displacement. It's called as the amplitude of the vibrations. A stands for the amplitude. A stands for the amplitude. And here it is basically the radius of a circle. That means it is the maximum displacement it can take place. You're getting the point. Beyond that, there is no possibility of having the maximum displacement. Okay. Hope it is clear to you. So this will give a better idea. So projection of a uniform circular motion on the diameter, okay, and the expression for the displacement. Okay, so I hope it is clear to you. Of course, this is not a part of VTU physics syllabus. This is just an course. This is just an additional topic so that the student can have a connection between omega and the linear displacement. Or omega are linear oscillations. Okay, so got it. Omega is meant for circular motion, while we are dealing SHM in a linear form. So how they are connected? So you can say that it is connected in this form. Okay, so I hope it is clear. If you have any doubts, students, you can call me back and clear your doubts. Thank you for your time. If you have any doubts, you can call me anytime. Thank you.